All right, good afternoon. Sorry for the unexpected absence on Tuesday. Feeling better. Just had some random stomach disagreement with something and was not able to stick around. So um, today we're going to talk about gas transfer fundamentals. On the bright side, I did have some extra time to grade, so I almost finished grading your exams. So should be by Tuesday. We'll talk about that a little bit then. And we'll also work on your homeworks. So we'll have feedback to you shortly. And yeah, so what were your impressions about the exam? How'd you feel? Not sure? Somewhat good? Somewhat bad? Okay. I don't think I've been doing it like a page at a time, so I haven't gone through any one person's total exam, so I couldn't tell you like people are scoring this or that, but I've seen how well you do on the first maybe 3 pages, something. Okay. Just not sure? Alrighty. Okay, well, we'll talk about it more next time, I think. So today we'll get into some new stuff. I guess maybe I ought to bring up the syllabus and kind of check in with where we're at. Might have to update it a little bit given last week. If I just miss one class period, I don't typically have to change too much. I will be out of town for this week, so I'm going to have to find an alternate solution. I will probably have somebody come give a guest lecture for one of those dates, maybe for both. So we'll keep you updated about that. But currently we're going to be talking about gas transfer and kind of how to apply gas phase equilibria and chemistry for water treatment, kind of as a nice encapsulation of both physical and chemical water treatment options, or on the flip side, air treatment, and then we yield a wastewater stream if we capture some contaminant that way. So sometimes it'll be more convenient to capture something out of the air and then treat it in the water, and sometimes vice versa. Sometimes it's okay to discharge something into the atmosphere and it's going to dissipate safely or whatever, and not be a problem. So kind of depends on the scenario, but sometimes we want to capture one or the other. All right, so after the gas phase, my plan is to do some adsorption discussions, hopefully get into some of colloidal materials. I might shift that around a little bit because I know I have somebody that could give you a nice advanced oxidation process lecture, but perhaps maybe I should give you some colloidal nanomaterial kind of stuff. So I'll be thinking about that, but that's kind of where we're at. Any questions or concerns? All right. So gas transfer. Typically, when we're thinking about water treatment, we have a few scenarios where gas transfer becomes really important. Some of them would simply be aerating. So for wastewater treatment, we have to supply our microbes lots of air so that they can do their thing, or perhaps sometimes prevent them from having air to have them do the other thing, right, to get anaerobic processes. Maybe we are applying chlorine gas as a disinfectant. We want to know how well is it going to dissolve, how do we model that, how much is going to be there. Ozone always is applied as gas, obviously. So many systems we can imagine if we are capturing or cleaning some kind of an air pollution discharge, so air emissions. Maybe we are capturing sulfur dioxide that's going to partition and dissolve into water as sulfurous acid. So we would want to understand that. Maybe we are eliminating volatile organic carbons from water or wastewater. So we are blasting air through it to strip it out of the water into the air and perhaps combust it there or treat it in some other manner. And ammonia stripping is another common use because of that transfer. So all sorts of environmental applications we can consider, and we really want to know, or need to know, what are the fundamental driving principles for whether or not a chemical is going to go from air into the air, right? So it's a phase transfer type of situation. Okay, a couple of more photos. Got a few photos here from our book. What we're looking at here is a bunch of diffusers for aerating. On the right, you see it in operation, filled with water. This is going to be some sort of an activated sludge basin. The bubbles are providing the microbes plenty of air and also a bunch of mixing. And this is maybe a good example of what these look like with a bunch of diffusers along a pipe. So wastewater treatment plants, typically a very large energy consumption source is simply blowers, blowing air through these tubes into the water. It takes a fair bit of pressure, and then you want to make small bubbles, get good gas transfer from them, and you have to do it constantly. So it's a lot of operational cost comes straight from the aeration. And so that's clearly it's important to get a good handle on that. Now, anybody know why it's not a good idea to go swimming in here or to fall in? Obvious reasons aside, because that would be very nasty. It would actually be quite dangerous to fall into one of these systems because of the bubbles, because it's essentially decreasing the buoyancy that you're going to experience. So if a large fraction of the volume of water that you would normally displace by being in the liquid is suddenly air, then the effective buoyancy is now a lot smaller. So you are going to sink, you're not going to be able to swim, you're going to have to walk your way, stumble your way to the nearest ladder and climb out. So in case it wasn't obvious, don't ever fall into a wastewater aeration basin. I haven't heard of a direct horror story, but I hear wastewater operators talk about it a lot, so I'm sure it has happened at some point, and would not want to be that person. At some point, you might just figure it'd be better just to die at that point. You know? Joking, of course, but okay. So, considering the cost of aeration, one thing people have tried in many situations is, well, can we game the system and do something cheaper than bubbling air? So our South Baton Rouge wastewater treatment plant actually has a version of this where you could imagine if we just pour water over some surface with high surface area, but it's also kind of open to the air, you can just allow natural gas transfer from the air onto a surface when you're doing all your reaction on a surface. This would be called a trickling filter. So you're just kind of trickling water over, I guess, trickling filter, or would be typical, over maybe some plastic material or some other sturdy, cheap material that you're going to let microbes grow on it and just have at it, right? This is going to change if you think back to our mass balances, it's going to change the way we'd model the reaction to be primarily a surface-driven reaction, kind of having that surface area concentration component into the mass balance instead of just what's happening in the bulk mixed system. So you can kind of get a picture that this is going to change a fair bit, but you could have the same processes happening. Microbes can grow, get enough of them. I think it takes a fair bit more space. There's some probably pros and cons. Probably going to have a situation where, I imagine there's going to be a bit more maintenance load in terms of, okay, what do you do once it's got tons of bacteria? How do you separate them? How do you collect the sludge and manage the sludge? All that. I don't have a lot of experience myself, but if that is something that is particularly interesting to you, I think Dr. Mo has a fair bit of experience with it, so he'd be a good one to ask more about that. Other aeration possibilities would be kind of mechanical. You can see here this wheel is just spinning in this thing. I've heard of things like raceway ponds where you have something inducing flow in the pond and also possibly kicking up the water and just spraying it up in the air and causing aeration, right? In fact, you can look at aeration in natural systems, streams and rivers, and model it according to some empirical parameters to say, okay, if it's this deep, this wide, these dimensions, and it's flowing at some velocity, what's the aeration constant? How aerated is this going to be? There's going to be a lot that goes into that, as we'll see. Temperature impacts our aeration. So there's several parameters, but anytime you have a lot of good mixing between your air and your water, whether that's like a waterfall or one of these things, you recognize that there's more options for aeration. You see a lot of ponds in Louisiana have fountains, and in addition to looking pretty, it's actually providing some aeration to what could otherwise become a rather stagnant and possibly bad-smelling pond, right? So it's sometimes useful to keep the ecology there in a nice state. Got a lot of organics in the sediment here, and it's just kind of bioreactors every time you see a pond. Okay, so in terms of the chemistry, essentially gas transfer is going to be driven by equilibrium. So quick refresher on equilibrium chemistry. If we were to describe a typical chemical reaction that has an equilibrium, maybe we'll take the example of CO2 gas, can dissolve in water. I'll just say with water here. Essentially what we will get is this will be in equilibrium with carbonic acid, H2CO3. And this type of equilibrium here will be what drives our gas transfer. Is it going to be in the water phase as dissolved? And in fact, maybe to be a little more correct, we would first write a step where we have CO2 aqueous, and then that plus water. It's not really that important to write it this way, but H2CO3. Okay, at any rate, the point is we can, on a chemical perspective, we can write these as reactants over the products. And we do that to say that we have some ratio between what is in the product form compared to what is in the reactant form for any particular equation where we have the reaction heading in both directions. So anytime we have a reaction heading in both directions, we will end up, once it reaches equilibrium, with some ratio between them. The equilibrium constant is going to dictate how far that ratio is from one side or the other. It would be a little bit like taking a seesaw and putting some weight on either side. And then if you move the center, you are shifting the equilibrium constant. Okay? So that would mean either to get them equal amounts, you'd have to have heavier weights on either side or whatever. You're shifting where the balance would occur, essentially. So you can think of this as K equilibrium, and you could have reactants and products. Don't think too hard about this, but if it helps you conceptualize what I'm talking about, that's good. That's my hope. So anytime we have an equilibrium constant, the generic formula for the ratio in a chemical sense would be the product of the products, each to their stoichiometric exponent. So just essentially taking the lowercase c here. If we were producing two CO2s and C is CO2, then we'd have a square there, right? A lot of times there'll be one if we have a simple situation. In this case, each of these is just one, and so on. So it'd be the products over the reactants set up in that manner using molar units, right? So we have to keep in mind these would be molar units. Anytime we have a liquid or a solid in these equations, we treat as unity. And we do that because if we have, let's say, water, I'll use that as an example for a moment. Water is in equilibrium with H plus and OH minus. That equilibrium constant, do you guys remember? This is one you should know or should learn and memorize. The equilibrium constant for water is what? A few of you took my course last semester, or last year, I guess. Okay, good. I heard it from one person. Does anybody else remember? Yeah. So this one, you all should know this, no matter what background you're coming from. Okay, 10 to the minus 14. This is what sets our pH scale to 0 to 14, right? And when we write this up as an equilibrium equation, we'd say K for water, because water itself is liquid and we're going to treat it as unity. This was all to explain why we're doing that. It will look like this. K is equal to H plus times OH minus. Therefore, if we're at a neutral pH, each of those are 10 to the minus 7, which is where we're getting pH 7. At pH 7, we're neutral. We have the same amount of H plus as OH minus. So just some reminders here, and you probably ought to remember that one. Now, the reason we treat it as unity is because if we're dealing with something at 10 to the minus 7 moles per liter, how many moles are in a liter of water? How many moles of water are in a liter of water? Anybody know? Yeah, it's like a lot more than one. If I remember correctly, it's more like 50, 55 maybe, but 20-something sounds pretty close. It's definitely not 10 to the minus something moles per liter, right? We have many, many moles per liter. So even at the very extreme pHs, it's a very small fraction of the total amount of water that either of those species would occupy. So at the end of the day, almost all of the water is still water molecules, H2O. That's the point. So that means if we wrote it up completely correctly for the case of water, we would be writing H plus times, we're writing the products, times OH minus over the concentration of water, of liquid water, but it just doesn't make too much sense. It's almost infinite in that sense. So we're just going to put that as 1. And that's that. Okay. I don't know if that's going to be too relevant for our gas transfer stuff, but just a little reminder, refresher about equilibrium in general. Liquids, and I guess maybe we do it for a pure gas, but liquids and solids, we definitely treat it that way. The point is we are describing the ratio between the reactants and the products. So if we have a gas phase system where we are looking at CO2 dissolving, we could describe the ratio of how much CO2 is in the liquid phase compared to the gas phase by a similar equilibrium constant. But these will be we'll label them differently. Okay, but that's kind of where we're heading with the core of gas transfer. So if we take a look, the book provides us this fancy, hard to read graph, and I only say hard to read because oh, this isn't the graph I was thinking. This one's okay. So at some point they're like giving us activities, and he's just like, look, it's pretty much concentration. Okay, so on the x-axis we have liquid phase concentration. So concentration of the liquid or of the dissolved species, and on the y-axis we have the concentration of the volatile species, the gas species. So in the gas phase. And so if you consider the ratio that I just talked about, we should get some idea that with a given ratio, these will track linearly, right? If I say to you that 2 times the amount of stuff is always in the liquid phase compared to the gas phase, then for every 2 we go along the x-axis, we should go up 1, right? Pretty straightforward. So let's take a look at what they're trying to show us here and say, okay, if this is the theoretical going across here, but then we have this actual gas-liquid equilibrium demonstrated by some example, I don't even know what species, it does this. And that's not linear, unfortunately. So what that tells us is we need something special to handle it. The first thing that we can do is to think to ourselves, well, is it linear sometimes in some ranges? And the answer is yes. In some ranges, we've got this section and this later section where it follows that rule, that expected equilibrium type of situation. Okay? And this is the distinction between the 2 gas laws you've probably seen at some point, Raoult's law and Henry's law. The difference is how concentrated is your system. So as we increase more and more concentrated with respect to the stuff that's dissolved there, we have to go from one to the other. And there's also a gray zone in between that we just have to do something empirical and do our best. Empirical meaning we take some observations and we say, okay, well, when I had this much, here was the ratio. And when I had this much, here was the ratio. So it's a trial and error type of thing instead of in a theoretical. So for Henry's law and Raoult's law, we can get kind of a theoretical, maybe thermodynamic, maybe some principled approach to get there. But if it's wiggly in the middle between, we just kind of have to figure it out. Okay, so the deal is at low concentrations or in a dilute system, we can use Henry's law. So if we're talking about treating drinking water and we want to know how much oxygen is dissolved in there, a Henry's law constant is probably the way to go. If we are dealing with some, let's say, pure toluene, and we want to know how much is in the liquid versus the gas phase, well, this is a very highly concentrated substance of the substance that I want to know is whether or not it's in liquid phase or gas phase. And here I just transferred away from the aqueous phase, by the way, so sometimes we'll have to do that. And in many cases, if we are in that type of scenario, we are highly concentrated close to this pure phase of some liquid. So when I'm talking about gas transfer, a lot of times I will say water, but really I should probably say liquid in many of the cases, because what we're talking about is gas transfer between liquid and gas phase. So for the example of toluene, if we had some sort of spill, chemical spill, and now it's in the groundwater, but it's like almost pure toluene, what are we dealing with, right? We have to use Raoult's law given that type of concentration, because it's going to follow it a linear trend up at that high concentration. So all that said, what do these look like? Well, Henry's law, we could say the concentration of the gas is equal to the concentration of the liquid times some Henry's constant. Quite simple. In fact, if we treat H as kind of like the K equilibrium that we were just talking about, then we would see, if we solve for H, this is going to be concentration for the gas over concentration of the liquid. That would correspond to writing an equilibrium equation according to our chemistry, just in the manner we were just talking about, with gas being the product, right? Products over reactants. So that would be a liquid phase going to a gas phase. That particular Henry's law setup would describe it that way. Okay? So it's a parallel in that sense. Oops. Now, we'll talk more about it, but there are actually many ways we could describe the concentration of our gas, and several variations of how we might use our Henry's law constant, just depending on what units we're using. So in practice, it's always going to boil down to something that kind of that simple. Didn't mean that pun, but that was a good one. Boiling. It's kind of what we're talking about today. But at the end of the day, it's going to essentially be fairly simple, just a matter of the units. All right, Raoult's law, kind of similar. Here we have concentration of the gas equal to a Raoult's constant, K, times the vapor pressure above the liquid times the concentration of the liquid. So here we're including the vapor pressure because it's no longer a dilute system, and we're going to have a big influence from how much gas is there. Another way to write that would be our pressure of the gas in total is equal to the vapor pressure of our specific gas that we're looking at times some ratio there. Okay, we'll get more into that. Okay, is this making some sense? So under some circumstances, we have a nice linear relationship, and we can follow that. So at low concentrations, it's linear, looks like this. At a much different concentration, the nature of the chemistry, the nature of how molecules are interacting changes quite a bit, and suddenly we have a linear relationship again. It's not necessarily the same slope or same constant or anything as here, but we do have a linear range where we can use another equilibrium constant of sorts. Okay, going to just elaborate a little bit more as we go on the different scenarios we might see things like this. I mentioned toluene. That would be one of many non-aqueous phase liquids, NAPLs. We tend to talk about light or dense non-aqueous phase liquids. This is where the Raoult's law type of stuff becomes pretty important. But it's just kind of a general, especially with respect to where are these materials within the soil. Now, Louisiana soil doesn't hold a whole lot of air. It's pretty fine particles. There's not a lot of room for anything else, but there is still some, and in many places with larger pores and things, there is actually some gas exchange even inside the soil, so long as you're above the groundwater table, right? So if you have a contaminant like a non-aqueous phase liquid, what's going to happen is it's going to fall, it's going to drain through the soil to some point. Once we get to the water table, then the density is going to kind of drive what happens next, right? If it's more dense than water, we could have something go lower. Some portion of it might dissolve. That would be an equilibrium process all by itself, liquid-liquid phase. Or most of it would probably float on top of the water. And then we have gas transfer between that light volatilization. So you get that vapor within the soil, you get this kind of showing the plume, right? We get the vapor around it, the plume itself, kind of some residual stuck on the soil, then the liquid plume traveling around on top of the water, and in this case, the light, the L-NAPL, some of it's traveling around. And then if we had dense, it would continue sinking until maybe finding some barrier to the aquifer, okay? So just kind of pointing all this out to explain a little more of when and where Raoult's law would be important. You can imagine environments like this, you would have to use Raoult's law. All right. Most of the time, we'll probably end up using Henry's law because most of water and wastewater treatment, we're probably dealing with drinking water or wastewater where we're aerating or something like that. Okay. So essentially, and here's the axes that I was kind of complaining about. On the y-axis here, we say we have gas phase activity. Activity, I'll remind you, is essentially a corrected form of concentration. So we can correct for how does the local environment impacting a chemical's reactivity with anything else around it. And so activity, lowercase a of some species, we would often write that as, let's say the activity of X. We would put it in curly brackets like that. And if it's very dilute, then that's essentially the molar concentration of X, because this will be essentially the same thing as saying an activity coefficient times X, and this activity coefficient is 1 in dilute systems. Or we can assume it is. So you've probably, if you've taken enough chemistry, you've probably seen activity coefficients and blah, blah, blah. It's something we can correct for. It's important if we have, let's say, salt water or even brackish water may be important. So sometimes it is quite important. But in general, and most of the time, probably all the time for us here, I would just call this the concentration. In this case, this is the gas phase. So I'm just going to put gas and the concentration of the liquid. So that out of the way, and we are in a dilute environment, at least with respect to this, the species that is going through this gas transition here. Then let's take a look at this scheme and learn what it's telling us. Okay, so this is describing the relationship between Henry's law, or described by Henry's law, including where the region is undersaturated or supersaturated. So as we have more gas going upwards, if we have more gas than Henry's law describes, are we going to be supersaturated or undersaturated? I might not have said it correctly, but the answer is up here, right? So let's interpret this. Actually, this is yeah. Let's take a look here and interpret it. Make sure we're on the same page and make sure I said it right. So the line itself is going to be the equilibrium, right? Where we've landed on the equilibrium, we have allowed things to equilibrate, right? There are moments where we suddenly introduce new air or whatever, some change, where we could have super saturation or undersaturation. So that's kind of how to be thinking about this. So if we give it enough time, we'll find that equilibrium. If we have, let's say, a higher ratio between gas over liquid, if this is greater than our ratio, when we're not at equilibrium, right, then essentially the solution will be undersaturated. And I think that's where my phrasing was leading at least me astray, and maybe you too. So if we talk about it with respect to the solution, we have more gas in the atmosphere near the solution than we would find at equilibrium. So that means the gas would like to go into the solution. Is that making sense? Okay. And if we're conversely, if we're on the other side of it, we are supersaturated and the gas wants to escape. So if we, let's say, refrigerate some water full of carbonic acid, and we allow all that carbonate, all this dissolved carbon, to be in the carbonic acid form by acidifying it, and then we suddenly heat it up, we're actually expecting that, and I'm kind of describing soda here, right? Expect it to go boom, because that gas really wants to escape. In fact, if we shake it and allow for better gas transfer, we're going to have an accumulation of gas, CO2, that has left the liquid phase and entered the gas phase and is now pressurizing our bottle. When it's dissolved, it's not applying really pressure directly, but it's might like to go to the gas phase. But if you shake a soda bottle enough, you might build up enough pressure, it'll go pop, right? So that's kind of, we intentionally put soda into a supersaturated condition. We acidify it to make the bubbles be able to come out, and yeah, that's kind of how that works. And we have, if we get it all just right, it's a little bit of bubbling, not too much, but a gentle force trying to reach equilibrium by degassing some of those bubbles. And that's what we like to drink, right? So kind of a little example there. All right, so let's talk a little bit about how physically this happens and what's going to be going on here. We can describe or I guess understand that the rate at which the gas will transfer is always going to have some strong correlation with how easy it is for these molecules to move around. Right? So the molecular diffusivity. Another way to say that is we would be diffusion limited at the interfacial layer. So where we have the boundary between phases, between gas and liquid, that turns out to be a very important location. And all of our transfer, all this dissolution or off-gassing or vaporization, whatever you want to call it, that reaction is going to happen within some layer, thin layer between these two. And we really have to understand exactly what's happening there in order to find out this constant. And in fact, these processes, this is the area that limits the rates and will kind of define the equilibrium constant in some sense. Just saying that if we have gas over here and liquid over here, just been writing the L as a cursive, so I guess I'm doing cursive now. And when's the last time you guys tried to write something in cursive? Well, that was not even it. Like, when's the last time you did it? This is the first time in a long time, aside from my signature, right? I write like oh, halfway? Ooh, that's scary. Anybody do this ever? Do you learn it in school? You do it sometimes? Still learn it? Okay. I don't know. I'm mildly proud of that one, but not very. Huh? Oh, they don't? lucky you, or unlucky, or something. I don't know. Anyway. Okay. So interesting. All right. Anyway, back to being an airhead. I mean, no. Okay. So if we have liquid and gas, we could consider what's going to impact molecular diffusivity on each of these, right? So temperature would be one of them, right? And in fact, the temperature of each piece could matter. So when I tell you that cold water stores more oxygen, there's a good chance that the reason for that has to do with the molecular oxygen's transfer between in this layer. I'm not actually sure that that's the case, but I'd be kind of surprised if that's not. I think it would have to do with this dynamic right here, because I think these two rates describing the rate at which it's entering the liquid or leaving the liquid are kind of determined by what's going on here.
I thought the reason cold water had more oxygen, had the capacity to hold more gas, was due to the way that the molecules are set up as water cools.
Well, that's kind of what I'm saying here, right? So if this distinction, the transport of oxygen in this interfacial layer here, is affected by how the molecules are interacting, that's kind of what you said, right? And so if that is slowed down or accelerated given some conditions, I think that's going to be dictating the equilibrium constant.
So obviously the interface between the gas and the liquid is where the gas is coming in contact with the liquid and vice versa.
Exactly. So yeah, if we're having oxygen come across, that would be what would matter there. So if we are keeping in mind that we have the competing rates of the gas entering the liquid or exiting the liquid, we could kind of consider the fact that we will have some liquid phase concentration. Then in that interfacial layer, that concentration will be changing as it's approaching the boundary. Likewise, in the gas phase, we will have some concentration in the gas, and then as it's getting closer and closer to that liquid, the concentration must change. So the width of this might be important. Clearly the sharpness of how different these are will be driving it'll be a gradient driving the force of wanting to move across this boundary. And overall, the dynamics here are what build our gas constant. Okay? And maybe drawing these rates here is, I guess that's probably fine. All right. Right, so we can look at this and we could go, oops, sorry. What did I do? Skipped way back. I was trying to brush some dust off my computer here. We could look at this in terms of a mass balance and include all of the components here. This is just kind of a reminder. We could look at what's happening across this boundary by looking at what's going in, what's going out, all of that. And anytime we're dealing with gas transfer stuff, of course we could do all these pieces. Now, in gas phase systems, diffusion becomes quite important, right? Especially compared to a liquid phase system. So these dispersion and diffusion things that we like to ignore if we can, and water systems may not be so appropriate. And so then you might have to dig a little deeper into our transport models for all of that. But in a general sense, let's just kind of take a look at what the book is showing us. We could have some control volume defined, and maybe we're looking at that interface of we were talking about a moment ago, or maybe some other system. But we'll have some rate of change of mass of our gas stored in the control volume is equal to how much is entering plus how much is, so that's entering by advection plus, so I'm sorry, this is going to be the net rate from advection plus the net rate from diffusion plus the net rate from any chemical reaction. And then here we're also going to add in entry from a gas transfer. So if we had a system that included both liquid and gas phase, and we were talking about what's happening in here, we could consider, all right, how much is entering from a flow rate? I have a batch here, so there's no flow rate. So in my little example here, we would say, okay, no advection. Diffusion and dispersion, well, again, batch, not really any of that happening, so we can get rid of that one. Then any reaction, so chemical reaction, let's say my little bit of chlorine left in here from the water fountain, maybe slowly decay. Okay, so we have some reaction. But then we might say, okay, well, is any of that chlorine happen to be lost from my water into the gas phase by volatilization? Maybe a tiny bit of chloramines or some fraction of the chlorine could be in the Cl2 gas phase. I really doubt it's much of any, but maybe we're losing a little bit, right? So that's the type of thing I'm talking about. So it's something that we could incorporate into a mass balance is really the point. Okay, so how do we make use of that in practice then? How do we apply these? A typical system, well, there are many versions. We've looked at a few. I wanted to give you an example of kind of an air stripper, or I think there's a few terms we could use, but one of these systems, air stripper would be a good one for this one. We have a situation where we have essentially a shower, and we're going to be allowing gas exchange from the water that's streaming down. You'd probably be applying water through a pipe like this into the system. So that would be your liquid flow, and then you'd have air being pushed upwards. This lets you just use gravity for the water, and it's kind of opposed by the air. That should kind of help with the mixing and making droplets kind of fly everywhere. And you have a blower at the bottom pushing air upwards, or your gas. So if your liquid is going down, air is going up, this can allow you, and then you'll catch the water and with some drain. Maybe you fill the thing with some material to improve the surface area or improve the flows, or maybe you design it in kind of a shower-like fashion, and maybe you have to get a slow enough flow rate or fast enough flow rate, whatever you need to get your droplets to act the way you want them to. But when you do all that, you get a nice exchange, and you can imagine, depending on the speed at which you're doing these pieces, that exchange could be pretty quick, or you could build a taller tower or something like that, adjust your flows to get enough time for that exchange to be sufficient. It doesn't take typically a long time to reach equilibrium for most things, but it's a good chance you're trying to get to that equilibrium, right? Okay. So a bit more about Henry's law. If we're trying to get A into an aqueous solution, and we write that as A aqueous is in equilibrium with A the gas phase, that gives us our Henry's law. Earlier we talked about, I said H is almost like K. Well, if we think of it as products over reactants, then essentially, in this case, what we're talking about is, and again, we could use activity here, but I'm just going to use it this way. Say that's a gas divided by a aqueous. Okay. In other cases, we might form strong bonds, and so then the chemistry itself, I'll say with already mentioned the sulfurous acid with sulfur dioxide. Sometimes we have to deal with those equilibrium reactions in addition to just the gas. So when we dissolve carbon dioxide, we get the carbonic acid, and maybe that's strong enough to affect how likely is it for our gas to leave. Maybe it's a little happier having a water molecule stuck to it and having that solvation or that reaction in addition. But oftentimes what we'll end up doing is kind of combining that equilibrium with the overall equilibrium between the gas and the liquid phase. Okay. Yeah, in a lot of cases, instead of, there aside from these special cases, usually you have O2 in the gas phase, and then you have dissolved oxygen as O2 aqueous. Right? We don't describe H2O3 as dissolved oxygen. We don't describe dissolved nitrogen as H2ON2, right? Usually it's just that gas, and that's that. But a few exceptions exist. All right. So, putting Henry's law to practice, I mentioned already there's a few formulations we could consider. Already reminded you a little bit about activity, but here we kind of see it again. So Henry's law, we would say H is this ratio, the gas phase concentration divided by the liquid phase concentration of some species at equilibrium. So the book is using all this nomenclature to say all of that within a valid region of Henry's law, so it has to be a dilute system. I guess we could put H prime and say that's the same thing but using activities and using the activity coefficients accordingly. But usually it's kind of nice to leave it as, just Henry's law. So one other thing I'll mention. I showed you that if we define H as products over reactants, and we compared something like, oxygen dissolving, right? So we would have to put the products as the gas. Now, that's actually not typical. The typical convention is to do the opposite, is to go from gas to the liquid, and the liquid or dissolved phase is the product. So by convention, we have the gas phase in equilibrium with the liquid phase. And the reason this matters is simply, are we having one over the other, or is it backwards? The way I've described it so far, I've allowed it to be kind of backwards, but I'm backwards from convention. But if we go with convention, then we probably need to revise and say, if we're going to call Henry's law an equilibrium constant, Kh, we should do 1 over the Henry's law constant to get it properly conventionalized. That's probably not the right way to use that word. To put it in terms of the proper convention. So if we want to use this equilibrium constant type of thing, the K, instead of just using H, if we want to use it with a K, according to convention of how we describe these systems normally, we actually have to say KH is 1 over H. Okay? At the end of the day, if we're tracking appropriately how we set up our problem or how we're setting up our system, this should come out with, the ratio. It should end up working out, and we'll recognize that. Okay, does that make sense? Fine on that? Okay, a couple other things. One is to remind you of the ideal gas law. So hopefully everybody's seen it, but just in case, the ideal gas law says PV equals nRT, and this is pressure times volume is the number of moles of this gas times the ideal gas constant times the temperature in Kelvin. Now, I bring this up because Henry's law will be given in all sorts of units, and we have to make sure that our dimensions are correct. So you probably also, if you've dealt with this much, this R constant can have different units depending on what type of pressure unit you're using for your pressure. So just a little warning, these guys can have different units, and I guess technically volume could too. Temperature is always going to be in kelvins, but this means that depending on how we're working with a system, we can put, just say can put H in different units, or KH. Okay, so it kind of ends up being whatever's convenient, which is a little annoying. But if you've done anything with gas phase stuff, you'll recognize that sometimes people have a ppm meter, sometimes you have some other formulation, sometimes you're measuring nanograms or leaving it in volume terms. Sometimes you're just simply reporting the partial pressure in a pressure term. So you can imagine it gets a little nutty. And so we just have to pay attention, make sure that our units are correct. So I'm going to read this little segment from our book. I think that'll elaborate a little bit. We can rewrite our concentration. This formula here is kind of a rewriting of the ideal gas law in terms of the number of moles of our gas. So, by the way, if you think about this equation, if you divide both sides by volume, you'll have moles per volume. Over here on the right, you could solve for moles per volume. You could also do something with the pressure there. So, if we rewrite the concentration of our gas, species I in moles per liter, it would be the number of moles per volume. And we can set that equal to P over RT. Okay, and the text here is essentially describing that. This means that the V would have to be the gas phase volume, should be in liters if we're doing moles per liter, exerted by I in the gas phase, and then we're going to describe that as the partial pressure of I. So if we have, in my bottle here, if we have half a liter of gas, and a small portion of that is CO2. CO2 has, let's say it's 400 parts per million or something. If we do that calculation, that's something like 0.4, or maybe I have that wrong, maybe it's 0.04% of that gas by volume is CO2. So the partial pressure, if it's at 1 atmosphere of pressure, would be 0.04 or 0.4 or whatever it is, of 1 atmosphere. So it'd be 0.04 ATM is the partial pressure of the CO2 there. Right, so you've probably seen these before, but just again, a reminder here. And we'll work some problems today if we have time, or next time, to kind of refresh the gas phase workings. Okay, T is going to be the absolute temperature, again, in kelvins. Okay. And just as a reminder, at standard temperature and pressure, we refer to that as STP. Our temperature then is 25 Celsius, which means that would be 298.15 kelvins and 1 atmosphere. Now, RT then, or excuse me, yeah, do we have, so at standard temperature pressure, the R times that temperature, we have a value of 24.47 atmosphere liters per mole, or this number, 2479 kilopascals liters per mole. So we could be using pascals, kilopascals, and liters could be using atmospheres, right? So the R here is changing based on which pressure unit we're using. And you can kind of see where how we describe the system might be convenient to have a different Henry's law for the units. So finally here, the partial pressure we can also say is the partial pressure is RT times the concentration of that gas. Okay, so here's a table of all the different arrangements that are commonly used for Henry's law and the dimensions that are going on. So if we have a mass concentration like micrograms of I per liter of gas, of course we're in micrograms, we have some particular symbol for Henry's law, and that will be, the units will be the liters of liquid per liters of gas. If we have molar concentration, that will be kind of the same deal. But if we're using partial pressure, our Henry's constant is going to be giving us atmosphere liters per milligram. Okay, so dealing with what we have to do, and this would be, that would be atmospheres for the pressure and milligrams per liter for the aqueous phase. Sorry, I didn't make that clear, but if we have partial pressure for the gas phase and moles per liter, then we have atmosphere liter per mole, right? So it's just relating the two based on what we've got. And there's a bunch of them. And depending on what we're using, this value of H, you know, at the end of the day, we are making a consistent ratio, but if our units are different, we might end up with a different value for the different constant to account for the units, right? Okay, does that make some sense? Yeah, okay. So just watch the units as always. And if you want to look at more, that's page 165 in the book. Okay, so here's a few examples of Henry's constants for some things maybe we see pretty often. And we've got it in a couple of forms. One would be the atmosphere per mole liter. We can flip back and say, okay, which one is atmosphere per mole liter? If I said that right. So this is probably partial pressure of atmospheres and molar concentration in the aqueous phase, I think is what we're dealing with here. So HPM, we could actually look that up. Yeah, that's this one. Okay, so they're giving us that one. That's going to be a pretty common one because we often use pressure in atmospheres. We often use moles per liter for our liquid phase, right? Okay, so nitrogen, that value is almost 1600. And let's pause a moment and interpret that. if nitrogen is the first on the list, the highest number, and acetic acid is the last on the list with the lowest number, which one has allows more of this gas to dissolve? I'm just comparing. I mean, you could use toluene, but let's just use acetic acid and nitrogen. You say more acetic acid will dissolve into the liquid. Okay. Now, acetic acid is maybe a weird one because it's usually in liquid phase anyway. But let's double check on that. So H here, this is going to be defining the concentration in the gas phase divided by the concentration of the liquid phase, right? And that's going to be giving us these units here. So if we have a large number, and I think the way I asked the question was not super helpful. If we have a large number, then most of it will partition into the gas. If we have a low number, most of it partitions into the water. So I agree. Yeah. So then we can kind of take a look here and think to ourselves, well, the gases up here would much rather be in the gas phase. And the species over here that have at least a gas form would much rather be in the liquid phase. Okay, so into the liquid phase, we wouldn't need so much aeration for our wastewater, right? It would be much easier for that to happen. All right, so that's just a kind of a little baseline example we can take a look at. Oxygen is more likely, or let's say less likely to enter the liquid phase than ozone. So ozone is actually a little happier to go into water, so that's kind of convenient in terms of ozonating. Chlorine gas is even a little better. That's also pretty scary. I mean, ozone's scary enough, but chlorine is, if you're ever working in the field of disinfection and you're ever dealing with chlorine gas, make sure you're really up on the safety stuff, because that's not good stuff to mess around with. Okay. Yeah. Okay, so let's take one problem here. So the Henry's law constant for oxygen at 25 Celsius, we just looked at it. It's given in that table as 769 atmospheres per mole per liter. So the task here is to express this constant A as a constant in atmospheres per mole per cubic meter, and B as HPC. I'll jump back in a moment and look at that. And C as the dimensionless Henry's law constant. So when I didn't mention this, but for dimensionless, if we essentially get the same units for both the gas phase and the liquid phase, we can make it dimensionless, right? So I'm going to flip back and give us the shortcut for this guy. Not the shortcut, but the definition. This one was atmosphere liter per milligram. how are we doing so far? First, A and B, pretty straightforward. Did I make any mistakes? Good. All right. So first couple, pretty straightforward because we're just simply doing some unit conversions here, converting from liters to cubic meters, converting from the moles to milligrams. That just requires the molecular weight of oxygen. 2 oxygens, each at 16 grams per mole. It's 32 grams per mole. Put that in, we end up with 0.024. We also have to convert for milligrams. And C is where we will need to be a little fancier. Don't really have time to finish this problem, I think, but we'll need to convert from our moles per liter into atmospheres or from atmospheres into moles per liter. Probably need to convert from atmospheres to moles per liter because the way that'll work out. But we have the ideal gas law, right? So we need to make use of PV equals nRT, which might mean we need to look up R and double check that we have standard temperature. So we would need to work from there to get the constant in that form. And I think that'll be a good spot to pick up next time. Any questions before we go? All right, so we'll leave it off there.